Welcome to 2025, where wood stoves are normally controlled by gravity. However, at Smokeless Chimney, we're working with the government to turn wood stoves into very clean burning heating appliances. Just about any wood stove currently in use today are using gravity and draft to make their fire and smoke go out the chimney. Well, I use fans, combustion air fans, and I want to share the algorithm that I use or developed. It's very recent. I worked over Christmas and New Year's to refine the algorithm. So I would like to share the algorithm, how it works, and how it makes beautiful fire. I've presented the algorithm in a chart. For different stove conditions, I'll put a different duty cycle in. Late in the burn, for a load of wood, it's going to be down around 25%. At the beginning, it's going to be around 100%, but it's a very tricky algorithm to decide what duty cycle is going in. But anytime I put a duty cycle in, it follows this pattern where it gets the fan spinning, it takes it up to the maximum, it drops it down to a 20% level, and then takes it up to its maximum again, and then spins down slowly, and there's a tail. And the tail's kind of important. The tail's for about the last 2 seconds. This graph is difficult to understand, but this is essentially what it looks like in the computer program. This algorithm is repeated several times a minute, and each time it's trying to tune the fire in. You can see the response in the next chart. I've got the stove temperature in blue, I have the stack gases in orange, and I have how the fan is responding. Each of those dots is a separate command sent to the fan. And, it's working pretty hard. It's always adjusting its airflow. This is 10 minutes of data showing the stove controlling and the stove temperature rising from 345 degrees up to 405 degrees over 10 minutes. We're even going to look closer. This is 1 minute of data, and you see the pattern in the orange fan signal. It's going up and down at a rate that we've determined really promotes good combustion in the wood stove. You can see that evident in the stove temperature in blue going from 401 to over 406. This is our opacity chart, and we see, or at least I calculated, during the first 15 minutes, we had only 3 minutes over 20%, and that is legal. The opacity combined with color shift gives us additional information on the smoke. Normally the shift is to the red, but we have higher color shift readings than we have opacity when normalized to nanometers of shift. This was a new light source, and I was pleased to find that it was native, or peak wavelength was between 5 and 600 nanometers. In the ASTM standard that I studied, they wanted light sources that were between 5 and 600 nanometers. It is not an easy light frequency to find, but I found a few, and this is their characteristic behavior, hanging in there around 580 and going up to around 710 on peak occurrences. In this beautiful chart, we have the wavelength channels coming into the sensor. and normalized for the first reading. So they stay as close together as they can. However, the blue tends to get scattered more. I call it the Tyndall effect. Some people call it the Tyndall effect. It hasn't been established that that's what's going on, but blue light does scatter easier. So you see the blue riding on top of the peaks and red not participating quite as much. This is the technical section where we're going to talk about thermocouple modules. For about the last few years, I've been using the MAX 6675, which is in the upper right hand corner. This is a fine thermocouple reader. I've got a lot of experience with thermocouples. They're very difficult sensors to work with because they use a very small voltage signal. They're not like RTDs or resistance temperature devices. These are thermocouples that use the Siemens characteristic to make a small voltage in dissimilar metals. And the trick is, at the computer end, you have to compensate for the cold junction. Now, the MAX 6675 was working pretty well for me, but I was having some problems with noise. When I put a thermocouple on a wood stove, it would change its output because of an electrical problem, the grounding of the wood stove. And I was talking to my team and said, hey, I'm getting a lot of noise, a lot of temperature fluctuations on my MAX 667 modules, and I'm not sure I can continue using these modules. They suggested I use the MCP 9600, which I have in the lower left-hand corner. I bought 5 of them, and I spent over Christmas, because I got these about the middle of December, and it took me a while to program them, but I was very pleased with the results. So the data from today's video is all done with the MCP 9600. Now, we don't get a picture of that data. It's not output to the data acquisition system. So all the data acquisition system is done with a very reliable data acquisition unit. But the control signal is done with the MCP 9600. And I'm going to go through that next. The issue I have is the MAX 6675. I have to use SPI, which is Serial Peripheral Interface, which uses 5 conductors. And I can't put it on the same bus as my I2C. And sometimes they would just stop working, and nothing had changed. So I wasn't really sure what I could change out the model, but that takes time. So I've only got about a month of experience with the MCP 9600, but it's an I2C device. I can put it on the bus with the display or the sensor, the light sensor on the Octoring, and it takes 3 milliseconds to get 2 temperature readings. One temperature reading is out at the end of the thermocouple. The other temperature reading is at the connection. And that's great. I can get 2 good, reliable, noise-free temperature readings, and I can work with that. So I'm changed my programming to work with the MCP 9600, and I'll show you that. I took photos to try to describe the growth of this fire. This is the first one at 9 minutes, and the fire in the right hand corner and the smoke output below. I'll go through the display. On the left hand side, we have the temperature inside or on the stove and / temperature in the room in degrees Fahrenheit. The next line down is 9 minutes. We're 9 minutes into the program cycle. So we're still in the first 30 minutes where it puts the most air in. The fan duty cycle is at 76%, and our T slope, which is our temperature slope, is a positive 11 degrees per minute. So this gives me a quick picture of what's going on inside the wood stove. Are we gaining temperature? Are we losing temperature? How far are we into the program? On the right side is the information coming in from the octa-ring. The octa-ring is the lower center picture, and that's about a 5 to 6% smoke output. So you can see with the tree in the background, you can see just a little wisp of smoke coming out of there. That's not a lot of smoke. For 9 minutes, that's pretty good. We are now at 16 minutes. The stove is 137 degrees. There's a picture of the fire. And we are at 6 to 7%, and you can see the wisps of smoke with the tree in the background. We are now 25 minutes into this. Fire is raging pretty good. The stove temperature, 248, room temperature, 69. We can back that up with the data acquisition system saying that stove is at 230, exhaust gases are at 525, room temperature is about 61 and 71. Our fans are putting out 4 volts, and we have a temperature slope of 12, so we're still gaining temperature. We got 81% duty cycle going to the fans, and we have a smoke output of 7 to 8. And you can see the picture I took at that time, not really very visible, but if you had to say there was smoke coming out of that chimney, I could say yes, there is smoke coming out of that chimney. This is the last set of pictures. Stove is at 455. Room temperature 74. We're 54 minutes in, 61% fan. We have a temperature slope up of 1 per minute and 12% emissions. We had just put a log in, and we have new fuel contributing. That's usually when you're getting a spike of smoke. You can see the 12% in the tree background there. There's definitely smoke coming out of that chimney at 12%. This was a lot of information to comprehend. However, I believe that we're going to have to manage these fires. I feel a lot more comfortable leaving the house if I know it's under my combustion air control system. I don't get smoke back into the house, and I don't have a lot of smoke leaving the chimney, and if I do, I know how much I've got leaving the chimney. This makes me feel better operating a wood stove in 2025.